Okay, so we've got here a revision video for unit 1.1, which is the first unit in the GCSE course. Now just a point before we start, this is a revision resource, okay, it's not a full lesson. I'll be spending a few minutes on each of these slides, but in reality each of these slides was probably a whole lesson in themselves, okay? So remember, there's no substitute from using the book and the lesson PowerPoint and the resources from class to make your own revision notes. Alright, these are just an aid. So, number one, first thing that Cambridge says you need to be able to do. Understand how and why computers use binary to represent data. Okay, so it's very common for people in exams to say they use binary because it's the only thing computers understand, which is true, all right, but we need to say why. Why do they only understand binary? Okay, so computers are made up of lots and lots of switches. Okay, these switches combine together and turn on and off in different ways to do everything a computer does. All right, now these switches can be represented as as a 0 if they're switched off, they're open, and a 1 if they are turned on or closed. Okay, so this is what binary data is. It's just saying that a switch is closed or on, or saying a switch is open or off. Right, so that's the ones and zeros, that's what they're doing. Alright, so they're saying 0, the switch is switched off, and 1, the switch is switched on. Alright, so that's the reason why computers only understand ones and zeros, because they're dealing with just an incredible amount of switches switching on and off that are controlled by logic gates, which we'll look at in another revision video. Alright, but that is why computers only understand binary. Alright, next we need to look at different number systems and just see if we kind of understand what they are. Alright, now the number systems we need to look at are denary, binary, and hexadecimal. Alright, so denary is a base 10 number system, and it's called base 10 because it uses numbers from 0 all the way up to 9. Okay, and this is the normal number system that humans use, that you use in maths, that you use to count with. Okay, then we have binary, which is a base 2 number system, and that is because we can use numbers 0 and 1. Okay, remember the switch is switching on and off, 0 and 1. And then we have hexadecimal. And this is a base 16 number system. And that's because it uses numbers from 1 all the way to 16. But it doesn't actually use the numbers to 16 because it also uses letters. And we'll look at that more closely on another slide. Alright, but it basically uses the numbers 0 to 9 and the letters A to F. Okay, which is why it's base 16, because there's 16 different varieties it can have. Okay, going from 0 all the way up to F. Alright, so the big thing that Cambridge says you need to be able to do for this part of the course is to convert between the different number systems. So you need to convert between positive denary and positive binary. You need to convert between positive denary and positive hexadecimal, and you need to convert between positive hexadecimal and positive binary. Okay, so we'll do a couple of examples, and we'll probably go from a denary number and take you through to binary and then to hexadecimal, and then we'll do a hexadecimal number and take it down to binary and then to denary. Okay, give me a second because my battery's going to go dead on my computer. I need to plug it in so it doesn't go off. It's plugged in. Okay, so let's just give a random number. Let's say we're going to do, the exam says it wants you to create 117. Alright, so we'll take 117, we'll take it into binary, and then we'll take it up to hexadecimal. Okay, so the first thing I'm going to do is write out my binary table, which is 1, 2, 4, 8, 16, 32, 64, 128. Alright, just remember it can go higher. You just need to keep doubling on the end. Okay, so if they ask for a number bigger than 255, you need to keep adding up 1 on the end until you get the number you want. Okay, they can ask you to go all the way up to 16, but they're far more likely to just ask for an 8-digit one like what I'm doing here. Okay, so the first thing we need to do is have a look and say, will 128 fit into 117? If the answer is yes, you put a 1. If the answer is no, you put a 0. In this case, it's no, a 0. Okay, because it's no. Then we do the same for 64. 64 does fit into 117, so you put a 1, and then you write 64 down here. Okay, then you just do 117, and you minus the 64. All right, which gives you 53. You look, does 32 fit into 53? Because that's our new number. Yes, it does. So we're going to put 32 down here. Okay, so now we can take away the 2 from the 3, which is 1, and the 5. Take away the 3 from the 5, which gives us 2, and it gives us 21. Now, does 16 fit into 21? Yes, it does. So we put a 1, and we put 16 here. So that now we do just 21, take away 16 to give us 5. Alright, so we've got 5 left. Does 8 fit into 5? No, it doesn't. Does 4? Yes, it does. So we do 5 take away 4 to give us 1. 2 does not fit into 1, but 1 does fit into 1. So that gives us our binary value for 117 there. Okay. Now, what we're going to do now is turn this number into a hexadecimal number. Alright, so we're going to use this table at the top here to do that. Now, the first thing I want to do is just put a line down the middle of this table. Okay, this side of the table I'm just going to leave as it is, but this side of the table I'm going to replace the 16 with a 1, the 32 with a 2, the 64 with a 4, and the 128 with an 8. Okay, and now I'm going to use this new table to work out each side of the value. Alright, so I have 4 and 1 to give me 5. If I look on my table up here, 5 is just 5, so that's fine. I can just write 5 there. And then if I look here, 2, 4, 5, 6, 7. So I can look at 7, and 7 is only worth 7, so I can write 7 there. All right, so my hex value, so this is my binary, and this is my hex. All right, this is my denary. Okay. Now, if it goes above, if we add this up and it goes above 9, right? So let's just say if I have a binary value, and I'll do, let's just do 1 1 1 0 0 1 1 1. Okay, so I can add this up. All right, so I'll just put just to show you 1 2 4 8 16 30. Sorry, I'm doing that now. 1 2 4 8 1 2 4 8. Okay, so 4 5 6 7. 7 is 7 on here, but here I've got 8 9 10 11 12 13 14. All right, so I need to find 14 on my hexadecimal table, which is up here, and that is E. Okay, so my hexadecimal number for this would be E. All right, so once I pass the digit 9, I revert back to the letters, all right, which represent that number. Now, you will not get given this table in an exam, so it's probably a good idea to memorize it, or just remember that once you get to 9, 10 is A, 11 is B, and so on, and it goes all the way up to F. All right, because they won't give you this table in the exam. All right, then let's have a look. What if they give you a hexadecimal value, and the hexadecimal value is something like 1011 1111. All right, what am I doing here? Sorry, I did that. Some hexadecimal value. It's a binary value. What if they give you a hexadecimal value of A C? Okay, so that's the hexadecimal value that they're asking you, they want you to work out. So what you need to do here is write 1, 2, 4, 8, 1, 2, 4, 8. Okay. And if you want, if it helps you, you can put a line down the middle. All right. So we're going to put A, and if the number on the left side is going to go onto the left side of your table here as well. So we look at A, and what is A worth? It's worth 10. So we make 10 here. All right. So we make 10 like that. 8 plus 2 is 10. Then we look at C. C is worth 12. So 8, 9, 10, 11, 12. So that is the binary. Okay. Once we've got the binary, we just replace this side with our original binary table. Okay. So we go from 8, 16, 32, 64, 128. Now we can just do the sum, 128, because that's that, 32, which is that, 8, which is that, 4, which is that. Okay, and we can just add it up just like you would do in primary. Okay, so you can say 8, 16, 17, 18, 19, 20, 21, 22. Right, so put it on the doorstep, then do 3, 4, 5, 6, 7, and then 1. So the answer for this would be 172. Okay, so that is changing denary numbers into binary numbers, and then into hexadecimal numbers, and then taking a hexadecimal number, turn it into binary, and then adding the ones up to get the denary for it in the end. Okay, now I have made other videos that explain that in probably a little bit more detail, and they are on the class website, and they're also in Google Classroom for you to look at. Okay, if you can't find them, if you let me know, I'll send you them and you can watch them. Okay, so next one. Now this one's another common question that you see in exam, and it's all about seeing how and why hexadecimal is used. All right, so it's been developed to benefit people, computer scientists. All right, and you'll see it in a whole host of places. All right, now the reasons it's used is, number one, hexadecimal is easier to understand than binary. All right, if you have a big long number and you can split it up into hexadecimal numbers, it's a lot easier and a lot more clear for programmers to read and write. All right. Number two, it takes up less space on the screen or the paper. Now, if you put this for a reason, if you get asked it in an exam, make sure you put less space on the screen or on a piece of paper. Because if you just say less space, that might sound like it takes up less memory space. And remember, hexadecimal is not about putting on a computer. It's about computer scientists using it to read. Okay, so it's less space on a screen or paper, not inside of memory. We're not really bothered about that when it comes to hexadecimal. All right, and it's also easier to spot errors, which takes me to some places you might see it. Now, the most common place you're probably going to see it is on a MAC address. All right, now we cover MAC addresses on a later revision video, and we did it in a different unit when we were studying the GCSE. But this is a MAC address on the back of, I think it's some type of computer device. I don't think it's a router. No, it's not a router, but it is a device that connects to a network. Okay, now this address, you can see here, every one of these digits is a hexadecimal digit, which means every one of these is 8 numbers long each, eight binary numbers long each. Okay, so you've got 8 times 1, 2, 3, 4, 5, 6. So you can imagine how long that would be to put on the back of a device to show people the number. And people would make mistakes very easily when they're reading it because it would be so long. So it's much easier to put in here. So that's a really common place you're going to see them, all right, as MAC addresses for network devices. Another really common place you're going to see them is in error messages on a computer screen, because errors are normally quite complex, all right, and each of these is a hexadecimal digit, as you can see by the numbers in there. Okay, so you can see how long that would be on your screen, and if you wanted to Google that to see how to fix it, it would be really easy to make a mistake and very difficult to read on your screen if it was that long. Okay, so two really common places you're going to see hexadecimal numbers. They're also used in color systems. right, for making colours, especially in web pages, all right, but in general in computers, the mix between red, green and blue would be done with a hex digit each. So you might get like FF 0A 2 3 or something like that. So that would represent this code of red, this code of green and this code of blue. Okay, so that's why we use hex, and some places you can expect to see them. Alright, so this one you might get asked to add 8-bit binary numbers and also understand the concept of what an overflow is. Okay, so let's just put the rules on first. Okay, so you have 0 plus 0 is always going to be equal to 0, and you can have 1 plus 0 is equal to 1, 0 plus 1 is also equal to 1, but 1 plus 1, which is 2, remember, sorry, let's put plus plus, 1 plus 1, which is 2, we have to write the binary for 2, which is 1 0, okay, which looks like 10, but remember it's not because it's binary. And then we can have as well 1 plus 1 plus 1, which is 3, which in binary is 1 1. Alright, so just remember these simple rules when you're adding them. Alright, apart from that, it's really quite simple. Alright, so we'll have a look now. Let's do maybe 1 0 1 1 0 1 1 2 3 4 5 6 7 8, and we'll do 1 2 3 4 5 6 7 8, and we're going to add these up. So we do 1 plus 1. Right, if we look at our rules up here, that is 1 0. So I'm going to put 1 on the doorstep and 0 down here, just like we would do in ordinary maths. 0 plus 1 is 1. 1 plus 1, again, 0 1 is 1. 1 plus 1, 0 1. Alright, so now we have 1 plus 1 plus 1, which is 1 1. 0 plus 1 plus 1 is 0 1. And now we have 1 plus 0 plus 1, which again is 0 1. But here, if you look, we've added two 8-bit digits up, and if we were doing maths normally, it wouldn't matter that we had this extra digit at the end. But what we've got here is we're dealing with 8 digits, which means we've got a byte of data to work with, and our answer should fit into a byte. But we are left with 1 2 3 4 5 6 7 8 9 bits left. Okay, now 9 bits left means that we can only fit 8 in there. We've only got 8. Computers aren't reasonable or flexible like this. If they want you to fit something into a byte, they won't let you make another byte unless you've told them in advance. Okay, so when this happens in your computer, when it's doing calculations, you get this. Alright, now this is an extra bit that it doesn't know what to deal with. It is flown over the limit of the byte, which is when you get your overflow error. Okay, that is an overflow error. So it's basically when your computer is doing calculations and it's left with a bit that goes over. Alright, so if you're adding 2 bytes up and you're left with a 9th bit, that's what an overflow error is. Okay, so this is how you add them up using these rules. Alright, and if you get left with a bit on the end here, it is called an overflow error. It means that you do not have enough memory to fit all of the data you have, so you've flown over. Alright, so another thing we need to be able to do is perform a logical binary shift, alright, with 8 binary numbers. Okay, so we'll keep this quite simple. 1 2 4 8 16 32 64 128. Right, so we'll just keep it nice and simple. We'll just put one number there. Alright, so we'll make number 16 in binary. Now a logical shift is just where you move all of the bits to one way or the other. Alright, so if I move it this way, this 0 drops off the end and doesn't exist anymore. If I move it this way, this 0 drops off the end and doesn't exist anymore. Okay, but every single number moves along. Okay, so if I'm going to move to the right, it means that the number is going to get smaller. If I'm going to move to the left, it's going to get bigger. Right? So if I move one place to the left and my number becomes this, right? Hopefully you've noticed that it hasn't just gotten bigger, it's multiplied by 2. Okay? If I move again, it multiplies by 2 again. Alright? But if I move to the right and I end up with this, you can see it hasn't just gotten smaller, but it's divided by 2. And if I go again, it will divide by 2 again. Alright? Now let's just say, instead of this first number that I've got, and I have already spoke about this, but if we have this, okay, and it moves along, these numbers will just drop off the end if I'm using 8 bits. Okay, so it will just be, if it was this number, it would just, this 1 would stop existing, or this 128 would stop existing. Okay, now the questions I have seen, now this is new to this syllabus, but the questions I have seen about it tend to say what will happen to this number if you make 2 logical shifts along. Okay, so remember, if it says 2 logical shifts to the left, you are moving everything twice. Okay, to the left. If it says 2 logical shifts to the right, you're moving it twice to the right. Alright, just rewrite the number in the exam. You'll have plenty of time. Just rewrite it, get the new value. Alright, and if it asks anything about what happened to the number or how the number changed, you can just comment on how the number is not the original value. Alright, it changes the value. Alright, if it's several marks, you can say that it changes the value. It multiplies by 2 on each left shift, and it divides by 2 on each right shift. Okay, remember, it's always best just to rewrite it, and remember, all of the bits move, not just one, or not just the ones, all of them. Okay, alright. Using 2's complement to represent positive and negative binary integers. Alright, so there's a rule you have to do here. Okay, you have to flip the bits, alright, and then add 1. Alright, that's the rule here. Now, they might be sneaky with you. They might say to you, represent the number 8 using 2's complement. Alright, if they say this, all you do is create your binary table: 1, 2, 4, 8, 16, 32, 64, 128, and then you create number 8, alright, and leave it. Don't do anything else, okay, because it's a positive number. Alright, now remember, all positive numbers start with a 0, all negative numbers start with a 1, okay, when we're using 2's complement. This is positive 8, it needs to start with a 0, alright, so you don't need to flip the bits, you don't need to add 1. But if the question is, let's make negative 8, now we need that 1 at the start, so we need to flip bits. So we flip all of the bits, make them opposite, and then we need to add 1. Okay, so we can't really add 1 at the very end here, so we need to add 1 to the total value. So the total value now changes to that. Okay, so that gives us our negative 8 in binary. And that is everything for Unit 1.1.